So this is the last screencast, and I want to talk to you in this screencast about vaccine development and how vaccines are made and the different types of vaccines, and also talk to you about some information literacy. So I want you to be able to know what kind of vaccines they are and what the pros and cons are of these different vaccines. And then I also want you to gain some information in terms of awareness of information, because during COVID-19 there was a ton of information floating around in the world, and a lot of it was actually fairly terrible. And we'll talk about how you can think about information that is coming to you. So different types of vaccines over the course of history of vaccines are things like live attenuated pathogens. This is a weakened form of a virus or a bacterium. It exposes you to the antigens without actually being strong enough to make you sick. The types of vaccines that are of this type are things like measles, mumps, rubella, chickenpox, and polio. An inactivated pathogen is a pathogen that has basically essentially been killed. It's either killed or inactivated form, and this includes our typical influenza vaccines, hepatitis vaccines, polio, and rabies. There are vaccines called subunit or recombinant polysaccharide vaccines. These contain specific parts of a virus or a bacterium, so it's not the whole organism. It's just a specific section of it that is the part of it that prompts an immune response. And these are the types of vaccines that are this type: hepatitis B, pneumococcal pneumonia, HPV, which is human papillomavirus, which is linked to cervical cancer, and shingles. The toxoid vaccine we mentioned in the first screencast. This is a vaccine to a toxin that is produced by an organism that causes disease, and so these are things like tetanus and diphtheria. And you'll notice that tetanus and diphtheria are both grouped vaccines. You get both of these vaccines together when you get a tetanus shot. Then we have viral vector vaccines. This is where we take the genetic material from a disease-causing virus, we put it into a harmless virus, and then that virus introduces the genetic material into your body. This is one of the forms of the COVID-19 messenger RNA vaccine. It's actually the least common form of the messenger RNA vaccine. The most common form of the COVID vaccine is just a straight RNA vaccine, where we basically take a specific segment of the RNA of the COVID-19 virus. We put that in a little lipid packet and we inject that into you. When that RNA gets into your system, it's incorporated into your cells, and then your cells produce the spike protein, and the spike protein is what stimulates the immune response. And this is how most of the messenger RNA COVID-19 vaccines were produced. And then we have conjugated vaccines, and these are vaccines that basically combine polysaccharides with a protein that basically acts like the cell receptors on the outside of a bacterium that then stimulates the immune response. So in all cases, these vaccines are trying to get an antigen into you to prompt an immune response. In some cases, the antigen is attached to a living organism. In some cases, the antigen is attached to an inactivated or dead organism. In some cases, scientists have just isolated the antigen and they're just giving you a dose of the antigen. And in other cases, they're giving your cells the genetic instructions to create the antigen so that then you're creating the antigen that then stimulates your immune system against the antigen. As you can see, those methods that are further away from a live organism are safer because you're not actually getting the live organism injected into you. So if you're just getting a little fragment of RNA that creates one protein that is the thing that stimulates your immune system, that's safer than getting an inactivated virus, because if the virus didn't get fully inactivated, the virus is now capable of making you sick. Conjugated vaccines, pneumococcal conjugate vaccine. So just to go back in history, Edward Jenner, 1796, took material from the blister of someone with cowpox and used that to inoculate somebody else. This was called arm-to-arm inoculation. This was a live version of a weaker pathogen. So cowpox is related to smallpox, makes you sick, but doesn't tend to kill you. But it's similar enough to smallpox that when you've been exposed to cowpox, you actually don't get smallpox. This produced an immune response to both cowpox and smallpox, and lo and behold, you had your first attenuated organism vaccine. In the United States, we declared smallpox eradicated in the United States in 1980. Toxoid vaccines, as I mentioned before, are vaccines to the toxin, in this case diphtheria and tetanus. These both came about in 1924. By 1930, they had a more effective version. They were combined in 1940. Pertussis, which is whooping cough, was added to the mix in 1949. And so now when you go and get a tetanus shot, you're getting both tetanus, diphtheria, and whooping cough. Thomas Francis and Jonas Salk in the 40s developed the first influenza vaccine. And then in the 1950s, Jonas Salk introduced the inactivated polio vaccine. Polio, if you are unfamiliar with it, was fairly widespread in the United States. It is a disease that affects your nerves and makes it difficult for your nerves to function, which compromises things like breathing. And so they would have to put you in this contraption here, which is an iron lung, which basically caused changes in pressure that allowed you to breathe. And it was debilitating. FDR was relegated to a wheelchair because of polio. And in 1955, they developed a vaccine for this. In 1955, there were 58,000 cases in the United States. By 1957, it had declined to 5,600 cases. So once again, a very successful vaccine. And this was the first major vaccination event in modern times that people really paid a lot of attention to. He tested this on himself and his family, and then the following year it got tested on a bunch of other people. In 1988, the World Health Organization started an eradication effort. By 1994, it was eradicated from the Americas. By 2002, it was eradicated from Europe, and now polio is only found in 6 countries around the world. After 1955, there were a number of vaccines that were developed. Heat deactivation of hepatitis B. We have pneumococcal pneumonia vaccines in the early 70s. We have hepatitis B in the 1980s. HPV vaccine in 2006. Ebola vaccine, which is the first messenger RNA vaccine. We oftentimes think that the COVID vaccine was the first messenger RNA vaccine, but of course we don't have Ebola in the United States, so we don't think about Ebola. But it came about in 2019, and then of course in December of 2020 we had the development of the vaccine for COVID-19. There have been setbacks. There have been recent increases in pertussis in the 1990s due to lower vaccination rates. And of course, we're seeing this increase in measles in the United States in the year 2025, once again due to lower vaccination rates. Vaccination is one of those things that's kind of like environmental protection. We forget how important vaccination is and environmental protection is because we've done a good job of getting vaccinated in the past. As a result, we don't see people walking around with measles and smallpox. And as a result, we don't think that we need to continue doing that because nobody has measles or smallpox until somebody does. And then if we have low rates of vaccination, those things can spread through a population because there's just not a large enough group of people who are vaccinated to stop the spread. So think back to the map of Texas where you have a small cluster of counties with low vaccination rates, and it spreads within those until it gets to an outer rim of counties that have higher vaccination rates, and then the spread stops at that point. And so keeping vaccination in the minds of people is important for health policymakers because we tend to get complacent when we don't confront disease all the time. So in terms of safety and effectiveness, there is a set of phases that you go through to develop vaccines. There's a lot of vaccine development. The first portion of this is done in labs. Before we ever start giving a vaccine to human beings, we test it on tissue cultures, then we test it on other kinds of organisms before we ever start giving it to humans. Once you've gone through this pre-development and you think you have a vaccine that works, there will be phase 1 trials, which is done on a small number of people. The main focus here is safety. Then phase 2 trials is done on a larger group of people, and the focus here is on both safety and effectiveness. Efficacy just means, is something effective? And then phase 3 trial is done on a larger group of subjects, but once again, the goal here is to look at both safety and efficacy. And with 3,000 subjects, you're more likely to see problems than if you're only looking at 300 subjects. Once everything has gone fine in the first 3 phases, phase 1, phase 2, and phase 3, then the vaccine is generally approved for use. And after it gets approved, then it's constantly monitored. So the vaccine adverse event reporting system is a system that you can log on to as just an American citizen and say, hey, I got this particular vaccine. Here's something that happened to me after I got the vaccine. I had, injection site pain or something like that. There's also the Vaccine Safety Data Link, which is a database where organizations all over the world, health organizations from all over the world, submit data about vaccine safety and side effects to this large database that then is accessible to everybody, which once again just makes the breadth of information coming in about the safety of vaccines even bigger. And then there's also this thing in the United States, the Clinical Immunization Safety Assessment, where they basically look at healthcare providers and doctors and things like that and solicit information from health professionals and hospitals and clinics about the safety of vaccines that are being used. And so even after a vaccine is approved for use, there is this monumental system of monitoring that vaccine as it is used more broadly in the population to detect any side effects that might be negative. The advantage of this is as more and more people take vaccines, you have this larger and larger pool of people to basically find really, really rare side effects that you wouldn't find even in phase 3 trials of the vaccine. So this comes to the next part and the last thing that I want to talk about, which is how we assess information in an information-rich environment. We live in an environment where there is tons of information. And one of my goals in having you think about COVID-19 in a scientific way is that you'll be better equipped to think about the next pandemic that comes down the pike. And there will be another one. In your lifetime, there will be a pandemic, and you can either possess knowledge that helps you make sense of stuff, or you can be ignorant of knowledge about how your immune system works, how vaccines are developed, et cetera, and then you're kind of at the mercy of people who might want to provide misinformation because it gains them something in some way. So I want to start this off by talking about how you sort through information that is available. First thing, know something about the topic. Hopefully you've learned something about your immune system. You've learned something about infection pathways for viruses. You've learned something about vaccines, how they're designed to work, how they're created, how they're tested, et cetera, that makes you more informed about this topic than you were when you started down this path. If you don't know something about the topic, you can always educate yourself. You can educate yourself by going to places like the Centers for Disease Control. It's a governmental organization whose sole goal is to keep Americans safe and healthy. Food and Drug Administration, another federal agency in the United States that is solely focused on keeping you safe and healthy. You can look in textbooks. You have a textbook available to you now that hopefully is of some use in thinking about these things. You can also talk to university professors, because university professors, they know a lot about the stuff that they teach. And so their goal isn't to lie to students generally. And so you can generally trust what they would be telling you. All of the stuff that I've put in all of these screencasts up to this point, you can go and look this stuff up in the primary literature or in textbooks, and you can see that what I've taught you conforms to what is known in the body of science. Another thing you can do is read things with a critical and skeptical mind. With this in mind, it might be better to read more than watch. YouTube, TikTok, Reddit, there are lots of places to get lots of bad information. There are better places to get information than online in user-created videos. And I realize that you're listening to a user-created video right now. And think about the characteristics of information you should trust. Is it sensational? Does it have a headline that is designed to scare the crap out of me? If so, you should probably go find something that is more rational. Does it come from a credentialed source? Does it actually interview scientists who don't have a particular horse in the game except making people not die? Does it seem like the information that you're reading is trying to manipulate you, or is it being communicated in a calm and rational sort of manner? And once again, go for calm and rational over sensational and manipulative. So just as a case study, I want to take you through something that I did a number of years ago. This was during the COVID pandemic. I was teaching a statistics class, and when I teach a statistics class, I try and make statistics relevant to students at the beginning of the class to show them that knowing something about statistics can actually help you understand the world around you. And at the time, we were teaching online, and we were in the heart of the pandemic, and there was all kinds of information out there. Much of it you could trust, and a lot of it you cannot trust. And there was a case study that was put out by the Centers for Disease Control looking at the effect of masking and whether masking was effective at preventing COVID transmission. And what happened was, at the time, the CDC was basically advising people to mask. And the federal government didn't want to impose mask mandates on people, so they left it to states. States didn't want to mandate masks on people, so they left it to counties. Counties didn't want to force people to wear masks, and so they just left it up to individuals, and then it just kind of became a free-for-all. But in some states, there were governors who did try and implement state mask mandates. Kansas was one of them. And the governor of Kansas basically set a mask mandate for July 2nd of 2020. And then the legislature responded by passing a law that said the governor can't do that. And so you had things like attorney generals essentially saying, we're going to sue people over mask mandates and things like that. And so what happened in Kansas was some counties adopted the mask mandate as the governor had asked them, and some counties in Kansas didn't. And so there was this kind of natural experiment where some counties implemented a mask mandate and other counties opted not to, because the legislature said that they didn't have to. And so you could look and see, well, what happened to rates of transmission after the mask mandate went into effect in those counties that adopted it versus in those counties that didn't adopt it. So it's always good to go and look at data. So you might ask yourself, well, what kind of data would you bring to bear on this question? Where would you go to find those data? How would you analyze those data? And so I first went to the CDC's website and I downloaded the article that the news report had referred to. And it was in the weekly morbidity and mortality report. And this is a copy of it, so you can go in and read it yourself. All you have to do is look for the morbidity and mortality weekly report, November 27th, 2020. And these are the data. So the light blue dots are in counties that adopted the mandate. The dark blue dots are without the mandate, and the dotted line represents when the mandate went into effect. These are 7-day averages, and so and they're taken every other day. So June 1st, June 3rd, June 5th, June 7th, June 9th. And they basically just went to the county health department database and looked at all the counties, and they're listed down here in the caption, all the counties that had mandates and didn't have mandates, and looked at the number of cases, and then they standardized those in terms of cases per 100,000 individual population. And what they found was that in the case of both counties, the rate of increase of cases was increasing over time until the mandate, and then after the mandate, in the non-mandated counties, the rate of increase was essentially unchanged, and the rate of transmission was flattened or reversed in the mandated counties. And so the mandated counties were increasing drastically in terms of the increased case rate. The number of cases per 100,000 individuals was going up, and it was going up at an increasing rate. And then it started to decline after the mandate. Part of that is that these are relatively urban populated counties, as opposed to most of these counties, which are relatively rural, and population density does have a role. Anytime you pack a bunch of people together in a closer environment, you will find that rates of transmission are higher. And so I decided, well, what I need to do, because I couldn't find the data set on the CDC website. And I realized, well, they're just accessing the state data. So I went to the state health records and pulled the case rates for all of the counties in Kansas for the period from June 1st to August 23rd of the year 2020. And I did this in December and January. They did this somewhat before that because they published it in November 27th and already had it all worked out. So what I did was I went to the website and I downloaded each county's data, and they don't have it all collated, so I had to do it county by county. It took me about 3 weeks of working in the evenings in my spare time just to get the data set built. And then it took me about another week. I had to learn how to do segmented regression. So I had to get the case counts. I had to construct the data set by county, dividing the data into counties with and without the mask mandate. I had to calculate 7-day rolling averages. I had to learn a new statistical technique, which I was unfamiliar with. It turns out it wasn't that difficult, but this all took me about a month of concerted effort to put this all together and get it analyzed. And then I had to do it. So this is all counties, daily cases, and one of the things that you will notice is that there's a pattern to the data. The lowest number of cases is always on Saturday and Sunday. Saturday, Sunday, Saturday, Sunday, Saturday, Sunday, Saturday, Sunday. And so this is kind of what you would expect to see in data that are real, temporal patterns that vary on day of the week. Saturdays and Sundays have fewer cases because a lot of doctors' offices are closed on Saturdays and Sundays, and so you just don't see as many cases. A lot of people go and see the doctor on Friday because if they're starting to feel sick on Thursday, they want to go see the doctor on Friday. They don't want to put it off until Monday. So one of the things that you can look for in data is you can look for signs in your data as to, is this a kind of pattern that I would expect in real data, or is this the kind of pattern that I would expect in data that are made up? And this kind of corresponds to what looks like real data. You can look at the days of the week divided by county, mandated and non-mandated. And once again, you can see that the low values are always on Saturdays and Sundays, and the rest of the days of the week are generally higher, except Monday. This is the daily cases partitioned once again by county into mandated and non-mandated, but these are just the daily cases. This is not the 7-day average. And so what you have to do is you have to, for any given day, you have to average the previous 7 days, and that's what goes in as the data point. And in my case, my data are going to look somewhat different than the data that were published because I did mine every day rather than every other day. But once again, you see that the red is the unmandated counties and the blue is the mandated counties. And 0 day is the day that the mandate took effect. And so we can spread that out and make it a little clearer by drawing a vertical line at the day that the mandate went into effect. And what we see is not exactly what was in the CDC data, but it's consistent with what was in the CDC data. You had strong increases in mandated counties before the mandate, a lower rate of increase, but still increasing in the non-mandated counties. But after the mandate, the non-mandated counties just basically stayed the same. That essentially is the same slope of the line as what you had before the mandate, whereas the situation in mandated counties, you basically saw the curve flattening. There were still a lot of cases, but they weren't increasing any longer. It was just kind of the same number of cases each day rather than more and more and more cases each day. And so I didn't see a downward trend, but I definitely saw a trend that is not significantly different from a slope of 0 here. And so implementing a mask mandate did reduce the rate of spread of the pandemic, and that rate of spread was essentially unchanged in places where there wasn't a mask mandate. Now, why does my graph look different from the CDC graph? And you can see the differences here. 2 reasons might be the way they divided up their data. Their data are done every other day, whereas my data are done 7-day averages calculated every day. The other thing is I was doing this in December into January, and most of it was done in January of 2021. And health departments are constantly updating their records. And so some counties may have had health departments within their county that hadn't reported data back when the CDC data were collected. And so my data are probably more complete and more accurate because that reporting that might have been missing at times when the CDC had gathered the data off of the website, those corrections might have been made. But in either case, the story is consistent. If you don't have mask mandates in place, cases are increasing. And if you continue to not have a mask mandate, that rate of increase remains essentially unchecked. But if you implement a mask mandate, the rate of increase actually goes down to a rate of increase of 0. You still have a lot of cases, but the number of cases isn't increasing over time. So, did masking reduce the rate of spread of COVID-19? It did in counties that had a mask mandate. And so if the question that you're asking of a health official is, I'm about to put a mask mandate on my citizenry, is there a good scientific justification for doing that? The data are fairly clear. Yes, there is a good scientific justification for doing that. Which then brings me to the last thing that I want to say about this, which is when someone tells you to do your own research, or when somebody says, well, I did my own research and I came to X conclusion, I'm pretty sure they didn't do what I did. And the reason is that 1, it's time consuming, 2, it's hard, and 3, you may not even possess the skill set to actually evaluate the claim and conclusions of that study from the Centers for Disease Control. I myself had to learn a new statistical technique, and I have a graduate degree in applied statistics, and I teach statistics at the college level. I teach statistics here at OU. And so whenever someone says, do your own research, realize that they're not referring to the kind of activity that I engaged in. It took me about a month to build this up and get it analyzed and come to a conclusion. It wasn't a month of full-time work, but it was a month of spare time work. And even then, I had to learn some things about how to analyze data in order to do it appropriately. And so that phrase, do your own research, that doesn't really mean do research the way scientists think of doing research. That means you'll watch 2 YouTubes and 5 TikToks and then you're informed. So my hope is that in the process of reading the things that you've been reading in your textbook and then also viewing these screencasts, you now know a whole lot more about disease transmission, infection pathways, your own immune system, so that the next time we do have a pandemic, and once again there will be another one, you have some basis of knowledge to help you evaluate this onslaught of information that is coming at us on a daily basis, so that you can make rational decisions about how you respond during that time that is inevitably going to come. So thanks for listening, and I hope you found it useful.